Okay, so now let us look at these two relations. V is a non-linear space and V star is the dual space. So for every f in V star, norm f in V star equals sup norm x less than or equal to 1 mod fx. Let me call this relationship 1, and we have, so x is in V of course. We just saw in the last corollary of the Hahn-Banach theorem that for every x in V, norm x in V is equal to sup mod fx norm f less than or equal to 1. So this x is in V, this norm is in V star, f is in V star, so I won't put the subscripts, and in fact this is equal to max norm f less than or equal to 1 f in V star mod fx. Let me call this relation 2. So let me erase the subscripts so we know where we are looking at, and therefore I don't have to put this. The first one is a definition. The second relation is a corollary. It came as a result of the theory. Now, if you, this is the starting point. So it says in the first one the supremum need not be attained, whereas in the second one the supremum is always attained and therefore it is a maximum. This is the starting point of a very interesting concept in functional analysis. This is called reflexivity. So let us take x in V and I define Jx in V double star, that means dual of V star, by Jx acting on any f is nothing but f of x, the evaluation of f on x. Then what does 2 imply? 2 implies that Jx belongs to V double star, and in fact norm Jx is equal to norm x. This is in norm is in V double star for Jx and norm x is in V. So the mapping x going to Jx from V to V double star is linear and preserves norms, and so it is called an isometry. In particular it is 1 to 1, and therefore it will map x V into a subspace of V onto a V subspace of V double star, preserving the norm. So this is called an isometry. So now we have an important definition. V is said to be reflexive if J of x going to Jx from is surjective. What does this mean? Every element of V double star, that is every continuous linear functional on the dual space V star, is actually nothing but an evaluation functional. It comes from V and it is just evaluation at that point. So this is what we mean by saying that the space is reflexive, and therefore this mapping is then 1 to 1 on 2 and continuous because it is an isometry, it is continuous both ways, and then you have that V can be identified with V double star. This will be an isomorphism. So such a space is called a reflexive space, and it is this particular mapping which should be subjective. It is not enough if V is isomorphic to V double star by some other mapping. We want this particular mapping, namely the evaluation functional mapping, which we have defined before, x going to j of x, that has to be subjective. So V, then you say the space is reflexive. So now if you apply relation 2 for V star instead of V, then you will get that the because of this isometry, you will get that the maximum, the supremum is attained in 1 also if the space is reflexive. So you just apply number 2 with V star replacing V, and therefore here you will get V double star, and that will be just V again. So this will become as if it's reflexive, then you get a maximum attained here also. So this, if you have a space which is reflexive, so if V is reflexive, sup equals max in 1 as well. So now there is a deep theorem of James. If sup equals max in 1 for all f in V star, then V is reflexive. So this is a necessary and sufficient condition. This we will not prove. So this is a very deep theorem in this. Now V, the dual space is always complete. So reflexivity occurs only in Banach spaces. If V equals V double star, if isomorphic through this mapping J, then automatically, since V double star is complete, V has to be complete. So the same notion of reflexivity is only there for Banach spaces. So now let us give an example of reflexive space. So example, let 1 less than p less than infinity, and then you look at little lp, which is set of all x which are sequences xi, such that sigma mod xi power p whole power 1 by p is finite. And sorry, you don't have to say this in the definition. And you have norm xp is equal to sigma mod xi power p I equals 1 to p infinity whole power 1 by p. So this is a Banach space, and we have seen this. So now I am going to look at, try to compute what its dual is and identify that. So let us take p star is the conjugate exponent. What does it mean? 1 by p plus 1 by p star equal to 1. So let y belong to LP star. So define for x in LP, Fy of x equals sigma I equals 1 to infinity xi yi. I am doing this in the real case. If it is a complex case, it will be xi yi bar. So that is a convention which we take. Okay, so we are doing everything in case of reals, but you can change it with yi bar, and whatever I am going to say will go through, and therefore we will just work with this. So then, is this well defined? Yes, because by Helder's inequality. So Helder, what does it say? That mod Fy of x, which is less, we already saw this example, this is less than or equal to norm xp norm y p star. So Fy is an element in the dual of LP, so it is in LP star, and norm Fy is less than or equal to norm Y P star. So I want to now show that every continuous linear functional on LP occurs in this fashion, and in fact this inequality is in fact an equality. So let now F belong to LP star, some arbitrary element of the dual. So now let EI be the sequence which is 0 etc., 1 in the ith place and then 0 etc. And you define Fi equals f of Ei. Okay. So now you have a sequence, let me put F bar, which is equal to Fi. So I have a candidate for an element in LP star. So the questions I am going to ask are, if F bar belongs to LP star, and can we say f of y x is equal to sigma I equals 1 to infinity f xi fi for all x in LP. And then thirdly, norm of f equals norm of f bar. So these three questions if we answer, then we will say that in fact the dual of LP is nothing but LP star. So that is why we have put this notation here. So we want to show this. So let n be a fixed positive integer. So we define xi in the following manner: 0 if fi is 0 and 1 less than or equal to I less than or equal to n, and mod fi to the p star by fi if fi is not 0 and again 1 less than or equal to I less than or equal to n, and then 0 again if I is bigger than n. So if you look at x, it is in fact of the form x1 to xn and then zeros, and therefore automatically, since it is a finite sequence, this automatically belongs to LP. Okay. So and further you can say x is equal to sigma I equals 1 to n xi ei. Therefore f is linear, so f of x equal to sigma I equals 1 to n xi f of ei, which is equal to sigma I equals 1 to n xi fi. But let me put what is the definition of xi. So xi is, it's either 0 if fi is 0, so we do not have to worry about it, and if you do this, this is nothing but sigma I equals 1 to n mod fi to the p star. Therefore sigma I equals 1 to n mod fi to the p star, this is less than or equal to norm f into norm x, and norm x in LP. So now let us compute this norm x is in LP. So what is norm x in LP? So if you have to take the pth power of this, if you take the modulus and take the pth power, then you get mod fi to the p star minus 1, that is what you get when you take the modulus, times power into p, and pp star minus p is nothing but mod fi to the p star, by definition 1 by p plus 1 by p star equal to 1, and therefore this is equal to norm f into sigma I equals 1 to n mod fi to the p star whole power 1 by p. So now if I take it, divide this over to the other side. So sigma I equals 1 to n mod fi to the p star whole power 1 minus 1 by p is 1 by p star is less than or equal to norm f. And now this is true for all n. This is an old trick which we have done. So this implies that f belongs to LP star, true for all n, and this implies that f belongs to LP star, f bar belongs to LP star, and norm f bar in LP star is less than or equal to norm f. Now further, if you take x is in LP, then if you look at sigma I equals 1 to n xi ei, this will converge to x in LP as n tends to infinity, because this is just x1, x2, xn 0, 0, 0. So I am truncating, and that's nothing but the partial sum series, and therefore it has to converge to the whole thing in this norm. Therefore what you have is, because of the continuity, f is continuous, this implies f of x equals sigma I equals 1 to infinity xi fi. In other words, f is nothing but f bar. We remember the notation which we used, fy which we defined like this. So therefore you have the same thing. So we have this. So, and what have we shown? We have shown that norm of f bar in LP star is less than or equal to norm f, and we also, so norm f is norm of f bar now, and therefore that is less than or equal to norm f bar in LP star, and therefore the two norms are equal, and so you have the norm of f bar in LP star equals norm of f in norm of f. So from this we have that, thus we have that LP star is isometrically isomorphic to LP star via the relation. So we have y going to fy. So fy of x is sigma xi yi. So now you can do the same game with p star. So similarly, LP star dual is nothing but LP, because 1 by p plus 1 by p star equal to 1. So the p is the conjugate exponent of p star is the conjugate exponent of p, and therefore, and you have the same relationship as this one. So this means that the mapping J, so we have that, so LP double star is the same as LP, and in fact the mapping J which I spoke earlier is nothing but the identity map, and therefore LP is reflexive. So this is an example of a reflexive space. So in the previous thing, as I said, we did everything as though it was real. So if we are looking at complex sequences, then you will define fy of x as sigma I equals 1 to infinity xi yi bar. Okay, and then the mapping now y in LP star going to fy in LP star is conjugate linear. What does it mean? You have that f of x plus y equals fx plus fy, but f of alpha x now will be alpha bar times f sub x. and so because of this conjugation here. And this is a conjugate linear map, but it's still an isomorphism. The mapping J is identity and it's on to everything else goes through. Okay, next example. In the same way we can show L1 star is L infinity. So given a continuous linear functional f in L1 star, there exists a y in L infinity such that f of x is equal to sigma xi yi, and norm f will be nothing but norm y infinity. Now if you start with L infinity star, is this equal to L1? Answer is no. So if I have y in L1, I can define fy of x is equal to sigma xi yi for all x in L infinity, and in fact you will have, therefore this defines a continuous linear functional by Helder, and you will have in fact norm fy will be equal to norm y L1, no problem. But there exists f in L infinity star which does not arise in this way. That is, there does not exist a y in L1 such that fy equals f. So let us give an example. So therefore L in L1, L infinity are not reflexive. L1 is not reflexive, sorry. This shows that L1 is not reflexive. Okay, and that later we will see that also means L infinity is not reflexive. So we want to produce a continuous linear functional on L infinity which will not come in this way. So let us take G in L infinity, all convergent sequences. So this is a subspace. So if x is in G, you map it to limit of xi, I tending to infinity, and call this as f of x. Then mod fx is definitely less than or equal to norm x infinity, and therefore f belongs to G star. So by Hahn-Banach, there exists a continuous extension to L infinity preserving the norm. Let us continue to call that as f. So claim f is not equal to fy for all y in L1. So you cannot produce a y in L1 which comes like this. Let us assume f equals fy for some y in L1. So now we want to get a contradiction. So you look at the following sequence: 0, 0, and then 1, 1, 1, and so on. So this is the nth place. So this is a convergent sequence, limit is 1. So f of xn equal to 1 for all n. So f equals fy And what does it mean? This is sigma I equals n to infinity yi. So 1 is less than or equal to sigma I equals n to infinity mod yi, and this is not possible. This is a contradiction since y equals yi belongs to L1. So if it's in L1, this is the tail of a convergent series, it should be going to 0, instead it is always greater or equal to 1. So there do exist continuous linear functionals on L infinity which do not come from L1, and therefore L1 is not a reflexive space. So in fact you can check this as an exercise. We looked at C0 in the exercises of the previous chapter. So this is all set of all x which converge to 0, and we saw this was a closed subspace of this. So it's a Banach space of its own. So show that C0 star equals L1 and L1 star is L infinity, and therefore you see, in fact using the same notation which we, namely f of x is equal to sigma xi yi. So this is how all these duals are identified, and therefore this space is Ln. So C0s and L infinity are not the same, obviously. This is strictly proper closed subspace of L infinity, and therefore this is another direct proof that these two spaces are not the same. I mean that L1 is not reflexive. Okay, so C0 star is L1, L1 star is L infinity, and therefore you have all these are all examples of non-reflexive spaces. But LP is reflexive for all 1 less than P less than infinity. We will see many other ways of proving this non-reflexivity of these spaces. So with this I will stop the analytic version, and so discussion of reflexivity, and which was also a consequence of the analytic version of the Hahn-Banach theorem. And so our next topic which we will take up now are the geometric versions of the Hahn-Banach theorem.